student who's in the foothills and is in need of a group. So if you're in that geographic area and can take on an additional person into your group, please talk to me during one of the breaks or after lecture. Okie dokie. So last time we talked about how, or where we left off was when we have a signal, we multiply it by a high-frequency cosine to produce a new signal, y of t. This x of t is typically voice, music, what have you. And you'll learn how to do this later in the class, but essentially every signal occupies real estate space both in the time domain and a corresponding space in the frequency domain. You've already seen that from the demos in the first couple of lectures. So let's say this signal x occupies some frequency band, let's say from B to minus B in the frequency domain. And we represent that footprint with the capital letter, and the variable now is omega. This is called the spectrum of x. Last time we showed how when x is itself a cosine of a much lower frequency than this cosine, how it shifts to the right and to the left in the frequency domain. Now, I got an email over the weekend. One of the great things about webcasting this class is that you get to hear from people all around the world who are watching the webcasts. So I got an email from Bill. Hi, Bill. Who I think is not watching the webcasts. He's listening to the podcasts. And Bill, if I forget to send you the link to the webcasts, please email me again. And he objected to something I said in the previous lecture. Maybe there was a misunderstanding, but I want to make sure that there is no confusion. I told you, in fact, even in the last lecture, that your education is a process of successive refinements. So one of the things I left off was the electromagnetic signal transmission aspects of this process when you want to send your voice signal over the airwaves. So there's actually an antenna here that takes this signal and sends it off. So Bill's objection was that I said the atmosphere attenuates low frequencies. That is actually true. The atmosphere attenuates pretty much all of the audible frequency range. But there is also an additional reason why we convert these signals into high frequencies. And that is that to build practical antennas with reasonable efficiency, you need to be in the high frequency range. And here's a crude, high-level view of what happens. So you remember from your elementary physics courses that the speed of a traveling wave is equal to its frequency times its wavelength. So this is the speed of a traveling wave. This is the frequency of the wave. And this is the wavelength. Okay? Electromagnetic waves travel at what speed? C. So for, let's go to another board. So for electromagnetic waves, that we amorously call E&M waves, V is equal to C, which is 300,000 kilometers per second, which is 300 million meters per second, right? Suppose the sound wave that I'm transmitting is my voice. And let's say I'm roughly at max around 3 kilohertz. So let's say F is 3,000 hertz. Okay? What's the wavelength? Figure out the wavelength. What is it going to be? Huh? 100? What? It's not a trick question. It's a simple arithmetic. Don't get worried. 100 what? 100 kilometers. Okay? Now, for reasons that are beyond the scope of this class, and you will learn these if you ever take EE 117, or undergraduate electromagnetics course. Antennas are inefficient at less than a quarter of the wavelength. What's the quarter of this wavelength? Which means, in this case, 25 kilometers. That means to efficiently transmit this signal, you need an antenna that's 25 kilometers long. And that obviously is a problem. Okay? We combat this problem by shifting the spectrum of my voice to a higher frequency range. And that's why we take the spectrum of my voice, let's say at 3,000 times 2 pi and minus 2 pi times 3,000 radians per second. Let's say that peak is 1. And we shift it to, let's say, somewhere in the kilohertz range or megahertz range or even gigahertz range. The reason you got such a long antenna, such a long wavelength, was that the frequency was low. So to allow for a reasonable length antenna, you need to shift this to a higher frequency, which makes lambda much smaller, which makes a quarter of a lambda much smaller, and therefore you'll have a reasonable length antenna. Okay? Actually, let's get rid of this kilohertz business. It's going to get confusing with the other one. So megahertz, gigahertz. So is that clear? It's a practical consideration. Now, this is only one of the practical considerations. The other consideration is that the spectrum is public property. It belongs to all of you and me. And it's the government's role to ensure that fair use is made of it by interested parties. So you have all these different radio stations, TV stations, and they all are vying for this valuable real estate space. This is valuable real estate space, the frequency spectrum. It costs money for a station to say, I'm going to get the privilege of using this particular frequency band. They have to pay. Now, how do you ensure that you can allow simultaneous broadcasts of signals without interference? By changing it? No, let's just stick with the frequency axis. So this is like a street, and you have different houses on the street. Well, I'm talking about this segment. Each of us, let's say 5 of us in the front row want to transmit radio programs all at once. Okay? How do we do that? So we have X1 through X5. X1, X2, all the way to X5. We're all roughly occupying this frequency band. You're engineer wannabes. How would you use this scheme to allow for simultaneous broadcasts? What would you do? Exactly. You modulate them with different frequencies. So, for example, you modulate this guy with cosine omega 1t, this one with cosine omega 2t, and this one with cosine omega 3t. Why am I putting parentheses here? So I have corresponding signals y1, y2, and y3. I shift x1 to here. So that's x1. I shift x2 to here. That's x2, capital. And I shift x3 to here. Okay? So now they're sitting at different bands along the frequency axis. Each of them pays their own fee to the FCC for the right to use those bands. And then at the, yeah. Yeah, there's always wave interference. This is all idealized modeling. There's always interference. Yeah, that's a huge problem. Yeah. This is the sterilized version of what happens. The core of what happens. Okay? So they send these. Now, at your receiver, you want to be able to tune to whichever one of these 5 stations that you want. And that's the part that we didn't get to last time. So that's what I want to briefly go over today. So you have x of t multiplied by cosine omega 1t. By the way, I haven't explained to you exactly how this spectrum, first of all, how do you get that spectrum? That's a topic for much later in the course. That's when we talk about Fourier transforms that maps a signal in the time domain to the frequency domain. For now, all I want you to think about is you have a signal, it has a footprint in the time domain, and it will have a footprint in the frequency domain. To also get the real story behind how this shifting occurs, you again need Fourier transforms. But right now we tell the simpler story by using trigonometric identities to see what happens. So here's y of t. I transmit that. Okay? Somewhere geographically different, that signal is going to come in. Now this is where I, again, idealize. Obviously there's atmospheric degradation, there's noise, there's attenuation, there's all kinds of stuff that happens in the atmosphere. But let's assume that y of t is received. It's a huge assumption. Let's say y of t is received. Last time, in answer to a question of how do you get this thing back, I said, well, at the receiver, you multiply by exactly the same cosine. So let's see, let's make this, what do you want to call this one? W of t. So I have y of t that's going out from the transmitter, which is x of t cosine omega 1t. Okay? I'm assuming the same signal comes in. I multiply it by another cosine. So what I want you to do is talk to your neighbors, use basic trigonometric identities involving cosine squared alpha and its relationship to cosine 2 alpha. And write the signal W in terms of the signal x and the cosines. That's what I want you to do. I'll give you 2 or 3 minutes. Yeah. Not quite. W of t will not be quite x of t. You'll have to do additional processing on it. And once you go through this, you'll figure out why. Okay. Meatball. Take your pick. Okay. So what's W? Take a step by step. Don't go to the final answer. So we're substituting for y, which is x of t cosine squared omega 1t. So we substitute this trig identity. So we have x of t. Okay. And now we multiply it through. So you have 1/2 x of t plus 1/2 cosine 2 omega 1t x of t. Now, last time when we took a spectrum and we multiplied it by a cosine, what happened to it? Split it into two. So let's do a bit of a review. Recall, xt times cosine omega 1t, which was our y of t, had a spectrum that looked like this. Each of the heights is 1/2 omega 1 minus omega 1. Right? This is the omega axis. And this is y of omega. Okay? Yeah? Yeah, that is the y-axis. No, this is a function in its own right. This is the frequency domain representation of the signal. So it's a function of omega.
So the 1/2 is
relative to the peak of where did I draw it? Yeah, x had a peak of 1. This was x. So let me draw that also so you know exactly. So x of omega, we assumed had some kind of a spectrum, and I just arbitrarily drew it this way. Peak of 1. And here you have omega 1 minus b, and that's omega 1 plus b, minus omega 1 plus b, minus omega 1 minus b. Okay? Now, we didn't quite show this story for an arbitrary spectrum. We showed it for when x was itself a cosine. But it doesn't matter. You take a spectrum of the original voice, you multiply it by a cosine, it halves the spectrum and splits it into two, sends one to omega 1, sends the other to minus omega 1. Remember, we made a big point about cosines and sines having not just one, but two frequencies. A cosine omega 1t has two frequencies, at omega 1 and minus omega 1. Remember the phasor story? If you don't remember it, you need to go review. And that's why you have a replica here and a replica here. One at each of the frequency content values of the cosine. So now, this was the story from last time. Here we have w of t, which is 1/2 x plus 1/2 cosine 2 omega 1t x of t. What do you think the shape of that is going to look like? W of omega. If x of t has this spectrum, what do you think 1/2 x of t will look like? And where will it be centered at? Centered at 0, height 1/2. Okay? B minus b. I'm going to stop writing these b's and minus b's because you get the idea. Then I have this term. I have x multiplied by not cosine omega 1t, but cosine 2 omega 1t. And on top of that, I have a 1/2. So what does that look like? Let's superimpose it in this picture. Very good. So you have one centered at, whoops, let's draw the figure to scale. Omega 1, 2 omega 1. You have a height of a quarter, because this, in the absence of this 1/2, you would have had x of t shifted to 2 omega 1 and minus 2 omega 1, scaled down by 2. But you also have that 1/2, so that makes this a quarter. And you have another box, another triangle here at minus 2 omega 1, a quarter. Okay? Now, if you had this magic system or wand or whatever you want to call it that would take this and would spit out x of t, what would it do? What would its behavior be in the frequency domain? What kind of an operation would you perform on the set of these three triangles to get back x of t? Don't use buzzwords. Filter what? So filter in or filter out? So you want to filter out the outermost triangles. Was there a question there? Okay. So one of the things you will learn in this class is filtering. And essentially, an idealized filter would take the triangle in the middle, pass it with an amplification factor of 2, and eliminate everything else. So these two triangles don't go through the filter. They get eliminated. So the high frequency content gets deleted. So in other words, you're taking W of t. Now this is a continuation of that diagram up there. Now W of t is sent through a filter that I'm going to draw the behavior of in the frequency domain. That amplifies everything that comes through it by a factor of 2. And these boundary frequencies can be, you have flexibility now because omega 1 is usually much larger than b. So this boundary, the cutoff frequency, can be as large as you want as long as it doesn't encroach into one of the other portions of the spectrum for W. So you can make it, let's just call it omega c for cutoff frequency. Okay? And what comes out? X of t comes out. Okay? So with some basic high school trigonometry, we've managed to actually crack through a very important problem in communications, which is amplitude modulation. Now, when you have multiple transmissions, like in this story, you are at the receiver and you've got a knob, or these days just a button goes up and down in the frequency, or a lever of some kind. What that lever does is it takes the local oscillator at the receiver to the appropriate frequency that you're interested in. So if you want station A, you go to the frequency, you turn the knob, and you go to the center frequency of that station, and then you'll filter it, and you're done. That's what happens in your radio. So it just modifies this frequency omega 1 at the receiver. And then there's this is called an ideal low-pass filter. Ideal low-pass filter. Yeah, the ideal low-pass filter usually has an amplification factor. Typically, we let it be equal to 1, but you can make it whatever you want. This kind of a filter, you will learn later, is not implementable in the real world. In the real world, a filter cannot have this kind of a sharp cutoff. Usually it rolls off. But those are subtleties that we'll come to later. Question? Yeah. So the notion of low pass refers to frequencies centered around 0, low frequencies. Band pass corresponds to any finite range beyond the low. That does not include 0. And then high pass includes anything greater than a frequency all the way to infinity for continuous time. For discrete time, it's a bit more subtle. But low pass, low frequencies, band pass, you can think of them as quote-unquote mid-range. High pass, anything beyond a number all the way to infinity. Those are the terminologies. So don't worry about them. We'll use them so many times you'll get them. You'll clinch them soon enough. Banzai! Take your break. Okay, folks. I want to do one more thing, bring to your attention another assumption that I made about this system. This transmitter and this receiver are at geographically different locations. Okay? It's a big assumption for me to say that I have an oscillator at the receiver that not only oscillates at exactly omega 1, which is the transmitter oscillator, but in fact, it's in phase with it. This is the real world now. Okay? I've assumed in this whole modeling process that the oscillator at the receiver has two properties. It oscillates at exactly omega 1, and there's no phase shift between this oscillator at the receiver and the oscillator at the transmitter. In fact, there's a third assumption, that the relative zero phase doesn't change throughout time. So these are all the things that real engineers and real companies have to worry about and fix. You get the sterilized version of the story, which makes my life easier too. But let's see what happens if, so what happens if the receiver oscillator is out of phase with the transmitter oscillator? In other words, I have a signal x of t. I multiplied it at the transmitter with a cosine, what do they call it, omega 1t. Y of t I transmitted. At the receiver, I got y of t. We already talked about how that's a big assumption by itself. But let's assume that I have a lossless transmission medium. But suppose I have a cosine omega 1t plus phi. This still has an assumption embedded in it. Two assumptions. One is that I'm still assuming that my local oscillator at the receiver oscillates at exactly omega 1. No two oscillators oscillate at exactly the same frequency. So this may be slightly off omega 1. It may, in fact, drift as a function of time. Somewhere it may hover in the neighborhood of omega 1. But let's say that it's exactly oscillating at omega 1. And the other assumption is that this phase itself is not a function of time, that it's constant. There are all kinds of assumptions we're making. But now we've at least allowed one level of approximation to the real world. So what happens when this has a phase shift? Figure that out. Write down the expressions you wrote down using this identity and tell me what you get. And tell me how this phi can ruin the party, can make it impossible for you to recover x of t with the scheme that we proposed last time. So talk to your neighbors. The process is pretty much similar. So you've got w of t is y of t cosine omega 1t plus phi. And this was x of t cosine omega 1t. So now you have the product of these. And I believe I have to give you a trig identity. So let me do that. didn't really need this, but in case it helps you use it. You can also do it by just expanding this cosine. How much more time do you need? 1 more minute. Okay. Shh. Meatball, pick the victim. You are?
I'm Patrick.
Patrick.
Okay, so when you include a
Yeah, walk us through it.
So WFT is YFT times cosine of omega 1 t times t.
Yep.
And expand out well, I did it using
The sum of these?
yeah.
Okay, let's do that.
So cosine of a plus b equals cosine a.
So you want to go from this stage? Where are you going to introduce x?
Or no, from the second.
From the second stage. So we have x of t cosine omega 1t times okay.
What you get from that is that first you can get,
See, the reason they're talking is that you're not loud enough.
okay, you can get cosine squared of omega 1 t,
Okay, x of t times cosine squared
which multiplies by cosine of t,
times cosine of phi.
and then minus x of t times cosine omega 1 t minus omega 1 t, which you can expand to 1/2 sine of 2 omega 1 t times sine of t.
Wait.
All that times sine of t.
Sine of phi. Okay.
So the first piece of the equation is the same as what we got before, which is the 1/2 plus 1/2 cosine of omega 1 t.
Mm-hmm.
And
But now there's this cosine of phi there. So how can this ruin you?
as phi goes to 90, then cosine of phi goes to 0.
Right. So
The second half of the equation,
wait. So pause. So the first part looks awfully similar to the previous situation we had. In the previous situation, though, this phi was 0. The two oscillators were in phase. So phi was 0. Cosine of 0 is 1. So all you had was x of t times cosine squared. But now you have a cosine of phi. So if this phi goes to pi over 2, or close to pi over 2, this term gets attenuated significantly. Okay, now what about this part?
second term, basically, when you have a cosine and a sine,
Mhm.
then that becomes 1/2 sine of 2 omega 1 t. And if you notice, there's no 1/2 factor in there anymore. It's just the 2 omega 1 t. It's just the pi to the main.
So tell me what the expression is. Let's rewrite the first part. So now you know why I gave you the identity. Because that would have put everything in terms of cosines. Minus x of t. And now what, Patrick?
1/2 sine 2 omega 1 t.
1/2 sine 2 omega 1t sine of phi. Okay. Now, so you have this expression. Where are the components sitting? You have a spectrum of x that's multiplied by cosine omega 1 squared t. And what do you know about that? What did the shape look like? What frequencies did it occupy? Around 0, and around 2 omega 1 and negative 2 omega 1. Okay? And then what? But now you have these cosine phis there. Cosine phi. There's a 1/2. There's a 1/4 cosine phi. And there's a 1/4 cosine phi. Now this is all qualitative drawing. And what about the what about the second term? So the second term has nothing in what we call the baseband. Which is basically the low frequency range. The second term has only stuff here and here. Okay? There's nothing in the center. There's nothing around 0 corresponding to this term. So you have this signal now. This is W of omega that you're sending through so you have the W of t. You're sending it through the low-pass filter. What's going to happen? What is the low-pass filter going to capture? The middle one, right? So it's multiplying it by 2. That's fine. What's going to come out? Cosine of phi times the spectrum of x. And that's where you get ruined. Because if phi is close to pi over 2, what comes out of the low-pass filter is going to be either 0 or something very close to 0 that you can't work with. You see the problem now? The phase shift between the local oscillator at the receiver and the oscillator at the transmitter affects the viability of this scheme. Now, some of you are probably wondering what the heck I did drawing this red triangle upwards and this one downward. Why is that? Sine, so you can roughly think of the cosine as e to the I omega plus e to the minus I omega. Sine is e to the I omega minus e to the minus I omega. There's a polarity difference between them. And I've actually cheated in drawing this, this triangle. Because sine, when you write it in terms of complex exponentials, has an I in the denominator. So it's actually the scalar on this red triangle here and the red triangle here is purely imaginary. But if you take the magnitude, you'll get the same triangle. The point is, this second component is a signal that has no content around 0 frequency. That's the important thing. Because multiplying by a sine takes the spectrum, shifts it to the right by omega 1, shifts it to the left by omega 1. Whether it does the polarity change or not doesn't make any difference. The fact is, there's nothing around 0. So there's no 0 frequency content or the neighborhood of 0 frequency content in this second portion. There is in this one because of the identity for cosine squared. We did this earlier. That's where this triangle comes from. Okay? So you have content around 2 omega 1 due to this and due to this. You have content around minus 2 omega 1 due to this and due to this. But the only content around 0 is due to the first term. And that first term is now hostage to this cosine of phi, the phase difference between the oscillators. And that's what can do you in with this scheme. So the whole notion of demodulating, so this is, you've heard me use transmitter. It's also called a modulator. And this whole system here is called a receiver or demodulator. It's a non-trivial problem to ensure that the oscillator at the demodulator is in phase with the oscillator at the modulator, at the transmitter. And there are ways of demodulating using a scheme different from this one. But it's a bit too early for us to talk about that at this stage in the course. So we've got about 10 minutes. So let's recap what we've been doing for the past few lectures. I told you there are some signals that are very important in everything we do in this class and in signal processing in general. Those signals were important signals. Those signals were e to the I omega t and its discrete time counterpart. So we've been talking about these. And of course, related to these are the sines and the cosines. And omega n and omega n. Okay? Also important are the yet to be defined impulses impulse in discrete time is very simply defined. I've done this already. It's 0 at n equals 0. I'm sorry, it's 1 at n equals 0, and it's 0 everywhere else. And this is called the Kronecker delta. And this is called the Dirac delta. It's a totally different beast. It's got nuances that we'll get into probably in the next lecture. And I'll just draw it for you. We denote it with an arrow, not a lollipop. It's 0 everywhere except at the origin where it's infinity, but the area under it is unity, and we'll go over that next time. It's called the Dirac delta. So far, we've been talking about sines, cosines, manipulations, their applications in modulation and demodulation. We talked about how this can be viewed as the position of a particle on the unit circle going around either clockwise or counterclockwise, and all of that. Now, in the next few minutes, I just want to point out that these sines, cosines, and complex exponentials belong to a family of functions called periodic functions. Periodic functions are signals. We've been tiptoeing our way around them, and I may have even mentioned the definition of a periodic signal in one of the lectures. But let's get this discussion nailed down so we can move on to the Dirac deltas. A signal is called periodic if there is a p, typically we take it to be greater than 0, such that when you shift the signal by p, you get the same signal back. And this has to be true for all t. The smallest positive t is called the fundamental period. The fundamental frequency associated with this signal is 2 pi over p, and that's called the fundamental frequency in radians per second. If you want the fundamental frequency in hertz, you simply, this is the fundamental frequency in hertz, or cycles per second. The interesting thing about periodic signals is that they can be broken down into sines and cosines and complex exponentials. And that's the whole basis of the theory of Fourier series that we'll talk about later in the course. Now let's do an example. So let's say I have a square wave. Now let's say this is 0, and this is 100 milliseconds. This is x of t. Periodic? What's the period? 100 milliseconds. And what's the fundamental frequency in hertz? 1 over 100 times 10 to the 3. Well, what's that? 10 hertz. And the fundamental frequency in radians per second? How are they related? Omega naught is 2 pi f naught. So you simply multiply that by 2 pi. You get 20 pi radians per second. Now let's do another one. Let's say x of t is cosine of t plus sine of 2t. Periodic? Well, I'm going to let you spend a minute with your neighbors. Tell me if this is periodic. If so, what the period is. Okay, Patrick's going to pick the next victim. Pick the next person. Before the end of class, Patrick. You are? Vincent? Benson. Okay, Benson. What have you got? You would graph it? Well, can you do it analytically? We want x of t plus p to be equal to x of t. Can you find the p? That's the question. So what is x of t plus p? What do I have to do on the right-hand side? I can't hear you. T plus p. Plus sine of what? 2t plus p or 2t? 2t plus p? 2p. Okay. So if this is we want this to be equal to x of t, what would this p have to be for the cosine? 2 pi. So 2 pi. And what about for this one? Pi. Can you find a p that satisfies the periodicity for both? For this to return to what it was, you needed 2 pi. For this to be equal to sine 2t, you need a pi. So what number can you give me that allows x of t plus p as a whole to be equal to x of t? 2 pi. So this signal is periodic with period 2 pi. Its fundamental frequency is? 1 radian per second. We'll give you a slightly more interesting problem next time. Go away. By the way, I need a group for the Foothills student. If you're in the Foothills, please talk to me.